I'm Payam. I'm a PhD student at Emory University and working under the supervision of Dr. Agichtein. And I'm going to present our participation at BioCADI 2016 challenge. So I will quickly go over the challenge, then talk about architecture, and then our design in more detail and experiment, and finally conclude the presentation. So we were given almost 800,000 dataset description, crawled from 20 different repositories. Each document consisted of a document ID, title, repository, and metadata. In the training phase, we were given 6 queries, and in the testing phase, we were given 15 queries. The evaluation metric was inferred in DCG. So there were some differences, major differences between a BioCADI challenge and regular IR challenges. You can see the first one is query intent. Basically, query intent is what the user is looking for. In regular IR challenges, the main goal is informational, which means the user actually wants the results. But in BioCADI challenge, the goal was more transactional, which means users want some information, which in turn answers another question. The second difference was query document mismatch, which means due to the nature of data sets, usually the query terms and the terms and keywords used in the document and in the data sets wouldn't match. And it was, on average, more challenging than usual IR challenges. And the third main challenge was the unusually small size of the training queries. So we did some steps to overcome these issues. For a query document mismatch, we did document enrichment using a field which we called metadata. I know there is some, actually, we could have chosen this name better, but anyway. We also used automatic query expansion using three-stage algorithm, and for answering small amount of data, we use a simple IR model called binary model 25, which actually has a small number of parameters, and usually it's shown that it's less probable to overfit. And also we labeled some queries which were given by BioCADI committee. It consists of 30 unlabeled queries. We did some shallow labeling, and I will discuss it in a few minutes. We also used learning to rank, but added few features to actually prevent overfitting of this model, because it's a machine learning. I will talk about it later. So I had some animation here. This slide shows our main architecture. We had 3-step retrieval model. We first input the query in the first step. Then using BM25, we retrieve the initial set of documents. Then we feed this set of documents into our expansion step, which uses 4 different external data sources and also a query expansion model called blind relevance feedback. Then we try to do retrieval using the reformulated query, and we use the resulting list to do re-ranking using learning to rank framework. So the main idea is, in the next step, we try to have a high precision using BM25. In the second step, we try to have a high recall because we are expanding the query. And usually it adds noise, but it's shown that query expansion can improve recall. In the third step, we try to, again, make balance between precision and recall using LTR. So we mainly use open source tools. We use Wikipedia and NCBI as textual sources. We use Google search, vertical search to extract the top document from these 2 data sources. And we also use KEGG HGNC. KEGG is Kyoto Encyclopedia of Genomic and Genes. It has a public API. You can access it. It gives you a higher level overview of between live organisms. HGNC is also a group which tries to set standards for human gene names. Using this data set, we try to extract synonyms for gene names. In the indexing phase, we tried to find some fields which can help at the retrieval time. So we indexed title, we indexed dataset description, which is officially named metadata. We didn't do any pre-processing, although we could actually go further and use the actually XML type and define more fields, but we just did some simple pre-processing and removed the labels. And we also added a metadata field, which I describe in the next slide. So for each repository, we tried to, back then there were just 20 repositories, we tried to extract manually extract some text from the website. You can see, for example, for NCBI, you extracted this text. The highlighted red words are the keywords that we thought they could help. So we added this text for each data set within each repository. So in more detail, imagine we have this query. This is the, query number 3 in the training queries. So we added to the documents downloaded from NCBI web repository. And we assume that there are some actually general keywords in the query which may not appear in the dataset descriptions themselves. So by adding that field, we hypothesized that those keywords may match the keywords in the query, and it could improve the performance. So you can see, for example, for this query, PIA10 is improved 50%, and NDCG also improved significantly by adding that piece of text to the documents which are grabbed from that repository. And the document by document analysis showed that the appearance of the 3 words gene, pathway, and cancer actually changed the distribution of words in the documents and matched the keywords in the query. And these 3 words are the main cause for improving this query. And it's just an example. I will later show that it's actually quite significant, and it generally improves other queries as well. So as a baseline, we use simple BM25, which is a probabilistic model, which tries to measure the probability of the relevance of query and the document. It has 2 parameters, which I later show that we tuned. It actually controls the weight of query term and document length. We also used Lucene multiple search to actually find the most important keywords in each document. So in the first step of query expansion, we use simple blind relevance feedback. It's the oldest query expansion method. It actually assumes that the top retrieved documents are relevant, and then extracts the most important keywords and adds it to the query. So it tries to relocate the query. You can see that, for example, if the original query is here, using those keywords, it can be relocated to the more positive documents. So in the second step of our expansion method, we tried to extract relevant and important keywords from external resources. So using those 3 data sets that I just mentioned, we extracted the keywords, and given the appearance of the most frequent keywords in those data sets, the appearance of those keywords in the top documents, we added those keywords to the query. So using this technique, we just try to reduce the probability of query drift. So the only condition was that those keywords must be present in the top retrieved documents. In the third step, we used query term weighting. Query term weighting is usually used when you have verbose queries. In the BioCAD queries were much longer than usual web queries. The usual length of web queries ad hoc ad hoc retrieval is 3 terms, but BioCAD queries usually actually had 16 terms. So the usual way in IR community is just to detect automatically the keywords and boost them using actually overweighting them. The technique that we use is called weighted information gain, which tries to actually measure the distribution of terms in the top retrieved documents. Using this formula, you can see that here you measure the distribution of each query term in the top retrieved documents and compare it by dividing to the distribution of that term in the whole collection, measure how much this term is effective in retrieving these set of documents. And the top top query terms are chosen and overweight. So we had 3 steps of query expansion. You can see we listed a few examples here. For example, here in query number 3, you can see we observe almost 100% improvement. The query is in black color. The original query, you can see that those highlighted words are chosen by weighted information gain. They are keywords. These are top 3 chosen keywords to be assigned a higher weight than other keywords. The terms in red color are chosen using external blind relevance feedback. You can see that, for example, this name is a gene name, which is relevant to cancer. Using blind relevance feedback, we added keywords such as cancer and tumor. And also, these keywords in blue are keywords that are added using external resources. You can see that we also have words like muscle or sequence. So the general idea is you detect the keywords, you add some relevant words using the data set itself and using the external resources. You can see also the last one, we observe decrease in the performance, which is usually called query drift. So far we talked about retrieval, expansion, and then in the third step, we used learning to rank. Learning to rank is a family of machine learning techniques which tries to actually use machine learning techniques for ranking. So the usual way is it tries to actually find the best combination of features extracted from the documents and use those features for sorting. For example, SVM rank, which is the well-known LTR method, tries to actually use classification for ranking. It tries to find the best, classify the pair of documents, and then reduce the number of misclassified pairs. We used MART, which is multiple additive regression tree. It combines boosting with regression trees and uses multiple regression trees to actually find the combination of features and sort the final document. So the usual way is you try to extract a feature vector using the combination of query and the document. Then you try to actually build the feature vector for the top documents, and then using the label queries, you train a model, and then at the testing time, you actually try to build the same feature vector for the documents and do the re-ranking. So here are some features, usual features in learning to rank framework. We use BM25, unigram, and bigrams. We also added 2 new features according to the necessities of the project. We used the distance from start, which tries to emphasize the introduction of the documents. So those documents which contain the query terms in their introduction will have a higher weight. And we also use the repository size. For example, we assume that if a repository contains 1,000 data sets, it must have a higher weight comparing to a smaller repository. And we actually, I will talk about it later and see how much these two features are effective. So far we talked about the architecture. Each step had some parameters to tune. You can see document title, body, and database info or metadata. For BM25, we have K1B and top documents, and for expansion and so on and so forth. We use grid search to actually find the optimal value for these parameters. We observe that here in this table, you can see the optimal weights for each field. You can see that the metadata that we had actually got the highest weight. And in this table, you can see that the external terms also comparing to the internal terms got the highest weight, meaning that more emphasis should be put on the external weights comparing to the internal weights. So in this table, you could see the final result. We used the results for steps before learning to rank. You can see that if we use BM25 without metadata, we get this NDCG 0.45. If we remove metadata, we will get something lower. Interesting thing is when we look at the P at 10, which is the most important feature in web search, the improvement is significant if we remove metadata. So in the next step, we add weighted information again to reweight and detect the keywords. You can see that the highest jump is observed when we add weak because of the length of the queries. Then we continued adding the steps using BRF and then external keywords, and then combining all together, we got the highest NDCG. So these results are actually got from fourfold cross-validation. We combined the official training and testing queries. So we also experimented with learning to rank. You can see that as it was expected, we have overfitting because of the size of the training. The NDCG is decreased using LTR, and it's significant. But what we did, we actually labeled the non-labeled queries given by the BioCADI committee. There were 30 queries unlabeled. We asked one of the biomedical students, PhD students, to label these queries. So for each query, we had almost 6 labels. Comparing to the official labels, which there were almost 1,000 labeling for each query, it's almost nothing. So we called it shallow labeling. So you can see that if we add those 30 queries with a very noisy judgment to the training set and retrain the LTR, the difference is significant. We can improve it a lot, specifically again for PAT10, which matters for search on the web. So it's interesting because we can approximate this process using implicit feedback of user and user clicks. So if we incorporate this step, we could use LTR more effectively. Here you can see the importance of each feature in learning to rank. Using feature ablation, you can see that as expected, BM25 got the highest rank. It's the most important field. But the interesting thing is the two new features, distance from start and domain weight or repository weight. The weight of these features are even higher than bigrams, which is interesting. So we tried different algorithm, vector space model, language models, and other methods, but none of them improved during the experiments over baseline, which is BM25 plus expansion steps. We also tried to use LDA topic modeling to actually enrich the features which are used in LTR, but we still didn't see any improvement. We also tried different learning to rank we tried different learning to rank methods, including RankNet and coordinate ascent, but we still got the same result. We didn't see any improvement, so we used MART. So future work, there are two main directions. As I talked, we observed a significant improvement over PIAT-10 when we used the shallow labeling. So one direction could be actually using implicit feedback to actually automatically have a larger training data. With that training data, maybe we could actually improve LTR. We could also use those features directly gathered from the user feedback into the features which are used in the LTR framework. And having more training data, we could also use other generalizations to reduce the query document mismatch using topic models and word embeddings. Another direction is using dynamic query expansion. For example, we could use algorithms like reinforcement learning to choose when we need query expansion based on the retrieved documents. So these are the main future directions. So conclusions. So we showed that enriching the dataset descriptions using metadata or information about the repositories can significantly improve the performance. We also showed that using the default settings, out-of-the-box settings for retrieval models wouldn't help, and they need some tuning for this domain. We also showed that keyword detection using Weak is effective. We also showed that extracting keywords from text-based resources significantly improve. So other than structured data sources, text-based data sources also can improve. We also observed that LTR is very prone to overfitting in this situation, and having a small amount of training data can actually cause LTR to overfit. But we also showed that using implicit feedback or having a noisy data, we can improve LTR and make it actually work in this domain. So this work was partially supported by the subcontract from the BioCADI challenge, and more details about the work can be found in the submitted journal to database.